Hello everyone, I am Dr. Brian Macon. In this section, we're going to learn how to solve trigonometric equations. And in this video in particular, we're going to learn how to solve equations that involve one trigonometric function. So let's get started. In this example, we're going to check if a given number is a solution of a trigonometric equation. This problem asks us to determine whether theta equals pi over 6 is a solution of the equation 2 cosine theta equals square root 3. And we are then asked if theta equals pi over 3 is a solution. First, let's consider the number theta equals pi over 6. Substituting pi over 6 into our equation, we write 2 cosine of the quantity pi over 6 equals square root 3. I like to put a question mark at the end because we're not sure if this equation is satisfied. That's what we're trying to determine. We know that cosine of pi over 6 equals square root 3 divided by 2. So our equation becomes 2 times square root 3 divided by 2 equals square root 3 question mark. As simplifying, we have square root 3 equals square root 3, which is a true statement, so I'm going to put a check mark next to that. Therefore, since the equality is satisfied upon substituting the value of theta equals pi over 6, then we conclude pi over 6 is a solution to the equation. Now let's check theta equals pi over 3. Substituting pi over 3 into our equation, we write 2 cosine of the quantity pi over 3 equals square root 3 question mark. So our equation becomes 2 times 1/2 equals square root 3 question mark. And simplifying, we have 1 equals square root 3, which is not a true statement. I'm putting a big X next to it to say it is wrong. So, since the equality is not satisfied, we conclude pi over 3 is not a solution to the equation. Now, just a quick note about the number of solutions of a trigonometric equation. If we isolate the cosine term in this particular equation, then we would have an equivalent equation of the form cosine of theta equals square root 3 divided by 2. Now, due to the periodicity of the cosine function, we know that there are infinitely many values of theta such that cosine of theta equals square root of 3 over 2. So, in general, when we solve a trigonometric equation, we want to find all possible solutions of that equation unless we're given a restricted domain variable. Let's consider a few more examples to illustrate this idea. In this example, we're going to find all solutions of a trigonometric equation. And this problem says the following. Solve the equation sine of theta equals negative 1/2. Give a general formula for all solutions, then list 8 of the solutions. Now we know that there are 2 values of theta in the interval of 0 less than or equal to theta less than 2 pi, for which sine of theta equals negative 1/2. Let's visualize the idea. Consider the following figure of an xy coordinate grid. We've sketched the terminal side of theta equals 7 pi over 6 that lies in quadrant 3. And we've also sketched the terminal side of theta equals 11 pi over 6 in quadrant 4. Now, reference angles corresponding to both angles have the side opposite of theta being a length of 1 and the hypotenuse a length of 2. Therefore, the terminal side of theta, which is the hypotenuse of each triangle, contains the point negative b comma negative 1 for theta equals 7 pi over 6 in quadrant 3, and the point b comma negative 1 for theta equals 11 pi over 6 in quadrant 4. Since we are told to give a general formula for all solutions, let's remember that the sine function has a period of 2 pi. So all solutions of the equation sine theta equals negative 1/2 can be written by the general formula theta equals 7 pi over 6 plus 2k pi, and theta equals 11 pi over 6 plus 2k pi, where k is any integer. Now, to list 8 of the solutions, we can choose any 4 values of k, and I'm going to choose k equals negative 1, 0, 1, and 2. So first, if k equals negative 1, then the first 2 solutions would be 7 pi over 6 minus 2 pi, which is negative 5 pi over 6, and 11 pi over 6 minus 2 pi, which is negative pi over 6. Next, if k equals 0, then we have two more solutions that would be 7 pi over 6 and 11 pi over 6. Next, if k equals 1, we're going to get 7 pi over 6 plus 2 pi, which is 19 pi over 6, and 11 pi over 6 plus 2 pi, which is 23 pi over 6. And last, if k equals 2, then we're going to get 7 pi over 6 plus 4 pi, which is 31 pi over 6, and 11 pi over 6 plus 4 pi, which is 35 pi over 6. Now we could use graphing technology to verify our solutions. On this screen, I have used a TI calculator and graphed the equations y1 equals sine x in the color blue, and y2 equals negative 1/2 in the color red. Making sure we are in radian mode, we've set the viewing window to be negative 2 pi to 2 pi on the x-axis and negative 1 to 1 on the y-axis. From the screenshot of our calculator, we can see one of the intersection points is highlighted, and the value of x given by the calculator is x equals negative 2.617994. And this is the decimal approximation of negative 5 pi over 6, which was the first solution we listed on the prior slide for k equals negative 1. Now, a quick reminder of how I would do this on the calculator is in y1, I would type sine of x, and in y2, I would type negative 1/2. So I'm graphing the left and right hand sides of my equation. I would hit the mode key and just make sure that I'm in radian mode. We can see on line 4 that we are. Then I would hit the window key and set negative 2 pi to 2 pi as my x-min and x-max, and my y-min and y-max as negative 1 to 1. Hitting the graph button, we now have the graph of y equals sine x and y equals negative 1/2. So to find the intersection point, what I want to do is hit the second button and the trace key. That takes me to the calc menu, and I'm going to choose number 5, which is the intersect feature. I get a blinking cursor. It's on the graph of y1 equals sine x. It is located at the origin initially, so I'm going to hit my left arrow a bunch of times to take me close to the intersection point on the sine curve, and then hit enter. Now it's giving me the blinking cursor on the curve y2. Notice that it's pretty darn close to that intersection already, so I will just go ahead then and hit enter. And then now it wants a guess. I'm going to leave the blinking cursor right where it's at and hit enter a third time. And then the calculator finds the intersection point for me as negative 2.617994. In this example, we'll be solving a linear trigonometric equation. This problem says the following. Solve the equation 2 cosine theta minus square root 2 equals 0 in the interval 0 less than or equal to theta less than 2 pi. Now this equation is considered linear because if we let x equals cosine theta, the equation becomes 2x minus square root 2 equals 0, which is a linear equation. Now keep in mind when we're solving a linear equation, we isolate the variable on one side of the equation. We're going to do the same thing here. When solving a linear trigonometric equation, the first part of the process is to isolate the trigonometric function. So for this example, our first step would be adding square root 2 to both sides and writing an equivalent equation of 2 times cosine of theta equals square root 2. Then we divide both sides by 2 and we have the equation cosine of theta equals square root 2 divided by 2. Now there are two values of theta for which cosine equals square root 2 over 2, and those are theta equals pi over 4 and 7 pi over 4. We could substitute the two values of theta into the original equation and verify our solutions, but I won't take the time to do that here. We could also use graphing technology. Here I have graphed the function y equals 2 cosine x minus square root 2 using GeoGebra in the viewing window of 0 to 2 pi on the x-axis and negative 5 to 3 on the y-axis. We're setting y equal to 0 to find the roots of our function, which are the solutions of our equation 2 cosine theta minus square root 2 equals 0. Our graph displays the two roots as x-intercepts, right, when y equals 0, at x equals pi over 4 and x equals 7 pi over 4. In this example, let's consider solving a trigonometric equation involving a double angle. Now, this problem says to solve the equation tangent of 2 theta equals 1 in the interval 0 less than or equal to theta less than 2 pi. And when we solve an equation where the argument of the trigonometric function is a multiple of theta, we will first find the general solution to make sure we list all possible solutions in the given specified interval. We know that tangent of pi over 4 equals 1, so the argument of 2 theta must equal pi over 4. In addition, we know that the general tangent function has a period of pi. So first finding the general solution, we can represent all solutions of this equation as 2 theta equals pi over 4 plus k times pi, where k is an integer. Now isolating theta by dividing both sides by 2, the solutions are theta equals pi over 8 plus k times pi over 2. We only need the solutions for 0 less than or equal to theta less than 2 pi. So substituting k equals 0, 1, 2, and 3, we find the 4 solutions that lie in the specified interval. That would give us theta equals pi over 8, 5 pi over 8, 9 pi over 8, and 13 pi over 8. Again, we could use graphing technology to graph y equals tangent of 2x and y equals 1 in the viewing window of 0 to 2 pi on the x-axis. From the graph shown here, we can verify there are 4 intersection points, and thus there are 4 solutions of the equation tangent of 2 theta equals 1 in the interval of 0 to 2 pi. Now, just a word of caution here we want to make a note of that whenever we are solving an equation for theta in which the argument of the trigonometric function is a multiple of theta, as in this example where we have the argument 2 theta, it's really important to write down all solutions first and then list those that are in the interval of 0 to 2 pi, or whatever interval is being requested. Otherwise, some solutions might be lost. In this example, let's solve a trigonometric equation. This problem says to solve the equation 3 times sine of the quantity 2 theta minus pi, from which we subtract 1 equals 2, in the interval 0 less than or equal to theta less than 2 pi. Now, since this is a linear trigonometric equation, we're going to begin by isolating the sine function. First, we will add 1 to both sides of the equation and write the equivalent equation 3 times sine of the quantity 2 theta minus pi equals 3. Now let's divide both sides by 3 and write the equation sine of the quantity 2 theta minus pi equals 1. At first, we're going to write the general solution to this equation so that we don't miss listing any of the solutions in the specified interval of 0 to 2 pi. Our last equation has the form of a sine function equal to 1. And we know that sine of pi over 2 equals 1. We also know the general sine function has a period of 2 pi. So we set the argument of 2 theta minus pi equal to pi over 2 plus 2k pi, for k an integer. Now let's isolate theta by adding pi to both sides. We write 2 theta equals 3 pi divided by 2 plus 2k pi. Then, dividing both sides by 2, we have theta equals 3 pi over 4 plus k pi. The values of k equals 0 and k equals 1 will provide the 2 solutions to our original equation of 3 times sine of the quantity 2 theta minus pi, from which we subtract 1 equals 2, in the specified interval of 0 less than or equal to theta less than 2 pi. Those solutions would be theta equals 3 pi over 4 and 7 pi over 4. And again, we could use graphing technology to verify our solutions. In the screenshot shown here, I have graphed y1 equals 3 times sine of the quantity 2x minus pi, from which we subtract 1, and it's in blue. I've graphed y2 equals 2, shown in red. We can see that we have the 2 intersection points verifying the 2 solutions for our equation.